In this lecture, I will present several functions in Mathematica that are useful for solving different kinds of equations that commonly occur in engineering and science problems. The first category of those equations are linear equations, systems of linear equations, which can be written in a matrix form, ax plus b, where A is a matrix and B and the unknown vector x are vectors. So these equations can be solved by inverting the matrix A, and the inverse of a matrix can be constructed in Mathematica using the function inverse. Vectors in Mathematica are written as lists of numbers delimited by curly brackets. For example, like this B, which I'm inputting as 1, 3, 5, a length 3 vector. Matrices correspondingly are lists of their rows, and so a list of lists, since each row is a list of the elements in that row, as this matrix A. The function matrix form is just a display function that makes it easier to see the structure of a vector or a matrix. Matrix form of B displays it in a column vector, and matrix form of A in a little box of numbers. To access the inverse of a matrix, you use the function inverse, and here I save the inverse of the matrix A in the variable a_inv. Then to construct the solution to the linear 3×3 set of equations in this example, I just multiply by A inverse times the right-hand side, and the matrix vector multiplication is simply a dot, that is a period. So A inverse dot B equals x. I save that value in x, and that's how I do it. If I want to check this solution works, then I subtract the right-hand side from the left-hand side and evaluate a dot x minus b, and I should get 0, which I do. Another category of equations that occurs often in science and engineering problem are nonlinear equations, and they are much more rich in their behavior than linear equations. In particular, you can have multiple roots. The roots can sometimes be complex, and in general they can't be solved analytically. Mathematica has several functions that are useful for solving such equations. Two in particular are nsolve, which stands for numerical solve, and findRoot. Nsolve tries to find all the roots to one or a list of nonlinear equations, and I'll give an example in a moment. findRoot is a procedure that solves a nonlinear equation but provides only a single root starting with an initial guess, and I'll show an example of that in a moment. So for nsolve, I'm going to solve this system of equations here. The form of nsolve is type the equation, comma, the variable that you're solving with respect to. Because I've already used x above and I want x to be a pure symbol without any definitions, I'm going to clear it with the function clear beforehand. Now you'll notice x turns blue here, which means x has no definitions that Mathematica knows because I just erased them. The equation, the form of it, if you look closely, you'll see that the equals sign in the equation is not just a simple equals, but it's actually two equals stuck together, and that indeed is how you type it, equals equals, and then Mathematica shrinks it down to this little double equals symbol, which is a little hard to see, but you must remember that equations are written with a double equals. So this nsolve will find the solutions to this cubic equation, and I'm going to save those in this variable roots, and so when I execute this, I get a list of what are called substitution rules. Each one is in curly brackets, and the entire list is in curly brackets, and each one of these basically says x is replaced by whatever the corresponding root value is, two of which are complex, as you can see. When you actually want to use those, well, first I can ask for the first one of them in the list, so roots sub 1, you might say. These double square brackets give me the first element of a list, and so roots sub 1 is the first of these substitution rules. And the way you use a substitution rule is in conjunction with an operator written /dot, and you can read that as substituted by. So f of x substituted by the first of these substitution rules will replace this x here with this value there. So f of x substituted by the first of the roots is f of minus 0.6, etc. Because f has no definition, Mathematica doesn't further evaluate this, and this is a good way of just seeing how this substituted by operation works with a function that has no particular definition. nsolve can also be used to solve systems of equations. Here I have two equations in two unknowns, y and x, and so in that circumstance you provide it with a list of the equations to be solved, again delimited in curly brackets, and a list of the unknowns to be found, again in curly brackets. And so if I evaluate this nsolve, then I get a list of two solutions, each one of which is a list of substitution rules. In contrast, the function findRoot, as I said before, searches for a numerical solution to one or more equations, but starting with an initial guess, and it will return only the solution which is in some way closest to this initial guess. So as an example of that, let's solve x over 10 equals sine x. To get a sense about what this equation is actually like, it's a good idea to plot it, that is to plot the right-hand side minus the left-hand side. And so I make a plot of exactly that over a certain range of x. And everywhere this function passes through 0, you can see that there's a root. So there's a root here, 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 here. So however many that is, 1, 2, 3, 4, 5, 6, 7 roots in this range of plot. And if I make different initial guesses, so for example, if I guess x around 3, then I'm probably going to find this root. If I guess x around 6, maybe I'll find that root. And so findRoot, the form of it is write the equation and then a list which is the variable and its initial guess. So as I say, if I make my initial guess 3, then I get this root here which is 2.8 something. If I make my initial guess 6, then I get this root here which is about 7.